Neutron stars. While the fate of lower mass stars is to become a white dwarf, high mass stars have two possible end states, and one of those is as a neutron star. Neutron stars were predicted to exist long before they were ever observed, and those predictions were based upon an understanding of stars and an understanding of physics. One of the conditions has to do with the mass of the star. An original star mass between 12 and 40 solar masses is necessary to become a neutron star. So we're talking about the higher mass A stars and all B stars will become neutron stars. Now recall that these higher mass stars ultimately end up with a core of iron. Well, that iron core needs to be somewhere in the range of 1.4 to 3 solar masses. Less than 1.4 solar masses, we know that that will turn into a white dwarf. So here we're looking at the next step up, and so we're looking at something that's more massive, has more gravity to compress, and it will become a different beast. In this case, it will become a neutron star. Now, our iron core was collapsing when we last left it, and we talked about that it would stop suddenly. But I didn't say what would stop that collapse. Well, what's going to stop the collapse of that iron core is what's called neutron degeneracy pressure. Now, our white dwarf was stopped with electron degeneracy pressure, where the electrons pushed against each other. Now we've got neutrons. We have actually collapsed to the point where protons and electrons have been crammed together to make neutrons. So we have actually compressed it to the point that the electrons have been pushed into the nucleus of the atoms and combined with the protons and have been turned into neutrons. When it gets to this point, neutrons behave kind of the same way that electrons do. They can't have the same energy in the same place at the same time. And so when you approach that, you are approaching degeneracy, but now for neutrons. Our white dwarf had stopped collapsing when it was about the size of the Earth. Now we've got 1.4 to 3 solar masses of material collapsed down to the size of a large city. And here we see it in comparison to New York City. So it's about the same size as New York City, a few tens of miles across. Our white dwarf, 1 teaspoonful, weighed something like 10 tons. A teaspoonful of neutron star is going to weigh about 100 million tons. Just crazy, insane densities when we're dealing with neutron stars. Neutron stars are small, obviously. It's about the size of a city. And relatively faint because they are small. So we can't see these. For a very long time, people did not believe that neutron stars existed. They thought it was just a strange mathematical phenomenon, but not reality. And it wasn't until the 1960s when the observation of pulsars finally confirmed the existence of neutron stars, because pulsars are neutron stars. It was eventually figured out, and that was finally the bit of information needed to confirm, in fact, that stars can become these very bizarre entities called neutron stars.